Okay, we need to talk about convergence of a series now, okay? We're going to be covering just what's on the AP exam, which means we're going to be skipping telescoping series. Telescoping series is neat, but not covered on AP. Okay, so infinite series is just when the terms of a sequence are actually added. We don't usually say infinite series, we usually just say series, okay? And the way that we denote a series is by writing the sum of the a sub n's, or if we want to be more specifically, the sum of the a sub n's from n equals 1 to infinity. Our starting value could be anywhere, but when, just like with sequences, if our starting value isn't indicated, we assume we start at n equals 1. So just like we were talking about with our improper integrals, now, we're not just looking for a pattern in the list of numbers here. We want to know if we sum an infinite number of terms, can that sum have a finite value? And we're going to see that there's a variety of answers to this question. Okay, so for the first one, I want to do the sum of the n's. So what that means is that you're going to add on, starting at n equals 1, I'm going to plug in 1 for n, and then add on, I'm going to increment by 1, so then I'm going to plug in 2 for n. And then I'm going to increment by 1, so I'll add on 3 in place of the n, and then 4, and then so on. So my series looks like this. So I have 1 plus 2 plus 3 plus 4 plus 5 plus so on. Okay, so that I don't have any curly brackets this time because I'm just, I'm not writing my sequences anymore. I'm writing a series. I have plus signs in between my terms to show that I'm talking about the actual sum of these values, and I have my plus dot 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 at the end to show that it goes on forever. Okay, so if I think about doing 1 plus 2 plus 3 plus 4 plus 5, is that going to be something that's going to have a finite value or an infinite value? Well, you guys know that's going to approach a value of infinity. Okay, let me just do that. Okay, so this would be a divergent series. Okay, if we look at example 2, I have the sum of 1/2 to the n. So please go ahead and list out the terms of that series. Pause and come back to me. So what I have here is 1/2 plus, right, I'm starting at n equals 1, and then n equals 2, I get a quarter, plus n equals 3, I get an eighth, plus n equals 4, I get a 16th. So this one isn't so plain to see. Will this series converge or will it diverge? Let's think about what this means. Okay, so let's say I have this blue sheet of paper, and I'm going to start by adding on a half of the blue sheet of paper. That would look like this. Okay, and that half of blue sheet of paper is going to represent the first term of my series. Okay, now I'm going to add on a quarter of my sheet of paper to represent the next term of my series. Okay, so I added on a quarter of the sheet of paper to represent my second term. Now I'm going to add on an eighth of the sheet of paper to represent the third term. Okay, so there's my eighth of a sheet of paper. Now I'm going to add on a 16th of a sheet of paper to represent my fourth term. Okay, so I just added on my 1/16th of a sheet of paper. Next I would add on 1/32nd of a sheet of paper, and then 1/64th of a sheet of paper, and then 1/28th of a sheet of paper. Okay, and I could keep doing this, and you guys can kind of see now what's happening is that I'm never going to get a full sheet of paper. It's always going to be like this little tidbit that's missing. Okay, I'll never get a full thing. Okay, so I can see that the sum of this series is going to get closer and closer and closer to a full sheet of paper, but never quite achieve a full piece of paper. But I still say that the series is convergent, and I'm going to say that the series is going to converge to 1. Okay, so I have two series here. One is divergent and one is convergent. Again, I'm not looking for a pattern to my terms. I'm looking for whether or not if I add on those infinitely many terms, if I'm going to have a finite value. Okay, so we need to talk about partial sums. A partial sum S sub n is the sum of just the first n terms of a series. The reason we're going to even talk about partial sums is because it is actually impossible to take an infinite sum. So I always have to stop at some point. Okay, so if I stop at the nth term, what would that look like? So S sub 1 is just going to be the sum of the very first term of the series, which would just be a sub 1. Okay, and then S sub 2 would be the sum of the first two terms of the series. So that would be a sub 1 plus a sub 2. Okay, S sub 3 would be the sum of the first three terms, a sub 1 plus a sub 2 plus a sub 3, and so on. S sub n would be the sum of the first n terms, a sub 1 plus a sub 2 plus a sub 3, up through a sub n. Okay, which I can just write instead of the sum from n equals 1 to infinity, the sum from I equals 1 just up until n of your general term a sub n. Okay, and this is pretty much the reason we talked about sequences to begin with. The partial sums are going to form a sequence which may or may not have a limit. Okay, so if you guys think about that, if my sum of a series is going to exist, if I keep adding on the first 5 terms, the first 10 terms, the first 12 terms, the first 100 terms, the first 500 terms, if those sums approach a number, okay, that list of sums approaches a number, meaning the sequence of the sums approaches a number, then the series will have a sum to it, okay? So think about that. Repeat what I just said if you need to. Okay, so what that means is that given a series, the sum of the a sub n's, a1 plus a2 plus a3, all the way on to infinity, let s sub n denote the nth partial sum, meaning I'm adding up the first n terms. If the sequence of the s sub n's is convergent, and that sequence has a limit, then, where that limit has a real finite number, then we'll think about what s would be for the series, and I kind of said it just before, but s would be the pause, the sum of the series. Okay, we're going to get more into the whole sequence of the partial sums and realize how limiting that is. But right now I want to shift gears a little bit and talk about geometric series. And you may or may not have talked about geometric series in pre-calc. Sorry that this looks like it's been to the funhouse mirrors, but a geometric series is the sum from n equals 1 to infinity of a r to the n minus 1, or the sum from n equals 0 to infinity of a r to the n. This is how your textbook has it. Okay, and what that is, if I start by plugging in n equals 0, my first term would be a r to the 0, and r to the 0 is 1, so I would just have a. And then my next term, if I plug in n equals 1 for r, I'd have a r to the first plus, and then my next term, plug in 2 for r, a r squared, and so on, and that would look like this. Okay, and I just said that a can't be 0, and we don't want a to be 0, because then my series would be 0 plus 0 plus 0 plus 0 plus 0 plus 0, which is probably the most boring series in the history of series. Okay, so we just say a can't equal 0. All right, I want to talk about a little, and what we're going to talk about in the next couple of minutes is, you don't really need to know, I just want you guys, it's kind of neat to understand where the formula for sums of geometric series comes from. So I'm going to do it real quick for you guys. Okay, so if r is 1, this series is also really boring. It would be a plus a times 1, a plus a times 1 squared, a plus a times 1 cubed, a. Okay, so all my terms would be a. That would look like this. Okay, and if I add on a infinitely many times, I'm going to have an infinitely large number or an infinitely large negative number if a is negative, but this is not going to be convergent. It'll for sure be a divergent series. Okay, if r isn't 1, then we have something much more interesting happening. So what I want to do is this. Okay, so I want to look at the nth partial sum here, which would be the sum of the first n terms. So a plus ar squared up until ar to the n. And I also want to work, and again, you don't need to be able to do this on your own. I just want to show you because it's neat where the formula comes from. So I'm going to take this s sub n and I'm going to multiply it by an r, and that would look like this. Okay, I multiplied every term by r, so I had ar plus ar squared plus ar cubed, and I have an extra plus sign in there, I don't know why. And then my last term would be ar to the n times r. If I add my exponents, I get ar to the n plus 1. Okay, now the thing that I want to do with these two things is I want to subtract them. Okay, and if I subtract them, on the left side, I will have s sub n minus r times s sub n, and on the right side I'm going to have a lot of terms that are going to subtract away. Okay, so I will my ar minus an ar, those are going to subtract out, and ar squared minus an ar squared, those will subtract out, my ar cubed minus an ar cubed will subtract out, my ar to the fourths will subtract away to 0, my ar to the n's will subtract away to 0, and I'll be left with an a minus an ar to the n plus 1. Okay, so the trick is going to be in manipulating this. So on the left side, I'm going to factor out that s sub n because that's really what I want to know. I want to know what my s sub n is so that I can find the limit of my partial sum. So I'm going to factor out an s sub n on the left side, and on from the right side, I'm going to factor out an a. And that'll look like this. S sub n times the quantity 1 minus r equals a times the quantity 1 minus r to the n plus 1. I'm going to solve for s sub n now. Okay, so I solve for s sub n, and I have a times the quantity 1 minus r to the n plus 1 over 1 minus r. All right, and one of the things that we said in the last little bit was that if the limit as n approaches infinity of s sub n is a finite number, then the sum will exist, the series will converge. So I want to take the limit as n approaches infinity of s sub n. Okay, so for the limit as n approaches infinity of s sub n, I have the limit as n approaches infinity of a times 1 minus r to the n plus 1 over 1 minus r. If you notice, if I'm letting n go towards infinity, the only part that this is going to affect. Okay, so this is the only part that has n in it. So if I'm taking the limit as n approaches infinity, I really want to let n approach infinity on this piece here that I've shaded. Okay, and this is the limit that I'm going to need to focus on. All right, if I think about when this limit will exist, and we're considering all values of r other than 1, right, because we already said up at the top that if r is 1, then we're divergent. Okay, but we're considering all values of r other than 1, and I want 1 minus r to a power to have a finite value to it. Okay, think about what kind of numbers I can bring to higher and higher and higher exponents that I will have finite values to as opposed to infinite values to, and we had a little discussion about this in sequences. Okay, so I want you to consider what would happen if r was greater than 1 or if r was less than or equal to negative 1. What would happen to this limit? Okay, so think about it and pause and come back. Okay, if r is greater than 1, so I'm taking a number even, 2 or 5 or 3 halves, and I'm bringing it to higher and higher powers, I'm going to have values approaching infinity. If r is less than or equal to negative 1, think about that. I have things that are alternately positive, negative. My limit's just not going to even exist. Okay, so in either of these cases, if r is greater than 1 or r is less than or equal to negative 1, my limit will not exist. The limit as n approaches infinity of s of n will not exist. And in these cases, I will be divergent. Okay, now, so let's consider values that, all right, I already ruled out r equals 1. I ruled out r greater than 1. I ruled out r less than or equal to negative 1. Let's talk about what happens if r is between negative 1 and 1. Okay, so if our r values are between negative 1 and 1, what would happen to the limit as n approaches infinity of r to the n plus 1? Okay, so you've got fractions between negative 1 and 1. Think about that limit, pause, and come back to me. Okay, if I fractions to higher and higher exponents, then I'm going to get numbers approaching 0. Okay, what does that say about the limit that I was interested in? Okay, so my limit as n approaches infinity of 1 minus r to the n plus 1, if r is between negative 1 and 1, and when r to the n plus 1 is approaching 0, I have 1 minus 0, which makes this limit equal to 0. Okay, so let's talk about the implications of that. So now I'm working with the fact that if my r values are between negative 1 and 1, this piece in here will approach 0. Okay, which means that if r is between negative 1 and 1, the limit as n approaches infinity of my s of n is just a over 1 minus r. Okay, and this is kind of big. So the limit as n approaches infinity of s of n is, we said, s. It's the sum of the series, and we're saying the sum of the series is a over 1 minus r. Okay, just to recap what we just said, if r is between, for geometric series, if r is between negative 1 and 1, or another way to write that is that the absolute value of r is less than 1, then the limit as n approaches infinity of s of n, which is the same as the sum of the series, is a over 1 minus r. Okay, what is a, what is r? Let's look at the series. Okay, a, if you look through here, a is just the first term of the series, and r is what you're multiplying to get from one term to the next. A times r is ar times r is ar squared times r is ar cubed, and so on. Okay, so for geometric series, if absolute value of r is less than 1, the sum of the series is a over 1 minus r, where a is the first term and r is the ratio between terms. Okay, I probably have time for one quick example with this stuff. You might have seen this formula in pre-calc, and if you did, then this is where the formula comes from. It's kind of interesting. Okay, so let's do one quick example, and then we'll cover the other examples in the second video. Okay, so we want to determine convergence or divergence, and if it is convergent, find the sum of the series. So all these series are geometric series, but one way for you to notice a geometric series is to realize that you're only going to see the n as an exponent. Okay, n will appear nowhere but your exponents. I'm realizing I'm cutting it really close, so we're going to pick up with these problems in the second video. So tune in to Intro to Series Part 2.